I'm Jim Heilman. Colleague is Kevin McGinnis. We've been in the department a long time, and we both are in the area of environmental physics. And the question should be, what does somebody in physics know about plant breeding? And the answer might be not much. So, but we do have some expertise that may be beneficial to you in terms of plant response to the environment, and particularly when it comes to water stress, water use, and plant temperature, and remote sensing. This seminar arose as a result of conversations that Kevin and I had with Dirk Hayes in looking at some of his plant temperature data and trying to interpret it in the context of what it might mean for high temperature stress. And one of the outcomes we hope to have from this 2-week presentation, notice it says this is part 1, Dr. McGinnis is going to continue on next week, is to encourage you when you're looking at plant response, doing anything with breeding that's related to stress and growing plants in different environments, to encourage you to take the biophysics course that Dr. McGinnis teaches. And also to understand that Dr. McGinnis and I are resource people that are available to you to be doing any kind of environmental measurements or studies in greenhouses where you're growing plants in pots in a greenhouse environment that's far different field, and you have any questions about that and what a proper experimental design might be to minimize the variability that you're inherently going to see, come and see us, because we might be able to help out in that regard. So we'll see if this pointer works. So one of the things that stimulated us is the idea of high throughput phenotyping, which involves screening large numbers of plants for things like drought tolerance, disease resistant, and so on, that tend to rely heavily on remote sensing technology and drones or ground-based non-contact measurements that might be measuring temperature. And with the notion that presumably these phenotypes are growing in the same environment, and I emphasize presumably for a reason. It's clear from these sensors that you can detect differences among phenotypes or among plots. The challenge lies in relating these differences to something that's relevant to a mechanism in the plant. You can go out and you can measure a temperature. What does that mean in terms of the drought stress of the plant? What does that measure? Where you measure a reflectance. What does that mean in the context of something that's relevant to the plants? And that's challenging because it's the physical environment in which the plants grow that is the primary driver of energy absorbed by plants and therefore plant temperature and water use. The environment in which plants grow is a driver. By the way, I want to keep this informal, so ask questions whenever they arise. Don't wait for later because I might have forgotten what was on the slide, the previous slide. And so we're going to look at this today and next week. And I already alluded to this, that applying results from greenhouse studies to field conditions is problematic because the environment in a greenhouse is far different in the world than in the real world. You're growing the plants in a potting mix that has different hydraulic characteristics than real soil, and you're restricting the root growth. So what happens in the greenhouse may not be readily applied to the field. Oftentimes you may think that you may have some plants set up to be well watered, you may think these plants are well watered, but if you actually went in and measured it, did a measurement of stomatal conductance, you would find out that the plants are already under some stress. So you run into some very unusual things that can happen in the greenhouse when compared to the field. So again, Kevin and I are a resource that you can draw upon if you need to. So, interpreting results from screening trials without a good understanding of the mechanisms of plant-environment interaction can lead to bad experimental designs, especially in the greenhouse, in the field. Improper measurements, especially when you're trying to relate what's happening to the plants to the environment in which they're going, and misinterpretation of results.
You just have to get notes.
They just sent you an email today? We were looking at...
Georgie, you want to mute your mic, please?
To reserve it.
Yes,
Yes.
Yes, we are in Washington. Juan Enciso and Yori da Silva. How are you doing? So, you just started or?
Oh, okay. There we go. All right.
Tell them to mute.
Georgie, can you please mute your mic?
That's what she's trying to do here. That's secretary trying to help us here.
So we're going to illustrate all this in the context of plant water use and water source. And we're going to be concentrating largely on
I hit mute up there. I don't know what else you can do.
When you say mute, you're turning off our mics from now. We need to turn off theirs. They should be able to hear us when we talk.
Yeah, you don't.
Well,
Let's make sure they can hear. Can you all hear us?
Yes, we can hear you.
Okay, we can you mute yourself? Maybe we can turn this.
Unplug the bar, turn the TV off.
You did, or do whatever you got to do.
There we go. Okay.
we can hear you.
Did you hear me okay?
Yes. Yeah, if you can talk.
Apparently, the mute is not working.
Yes, don't worry about it. Just don't talk.
Yeah, can I ask you just to remain quiet unless you have a question?
Okay.
Thank you.
That will work.
Okay, let me continue on. So they're going to start out with some basics. Plant water use is fundamentally controlled by the available energy. Water use is an energy-driven process. And by how much of that available energy is used to evaporate water at cell wall air interfaces. That drives water use. Plants are not suction pumps that are using as much water as they please. Water use is driven by the available energy and how much of that available energy is used to evaporate water at cell wall air interfaces. And the amount of available energy consumed by evaporation is affected by the amount of plant available water in the soil. And available energy and available water are interdependent. That might not be obvious right now, but hopefully it will be later on. And there are feedback mechanisms that cause that to be the case. And so immediately you should be thinking about, well, how do I separate what's happening in the above ground environment from a stress that may induce by soil water deficits? How do you do that? When the available energy is driving the water use and affecting plant temperature, and so is soil water. So we're going to start by looking at conservation of energy and the energy balance. We'll go through step by step to show how all of these linkages occur. And then I'm going to start asking you some questions, so take notes. The energy balance says that the energy into and we're going to do it this in the context of an individual leaf for the moment, that the energy input into a leaf is balanced by the energy output from the leaf to the environment and the amount of energy that's stored in the plant. So the energy that's going into the plant, some of that is being dissipated to the environment and some of that is being stored. And in the context of how we're going to describe that, we're going to say that energy in minus energy out minus energy stored, 0. Conservation of energy requires this to be the case. We have to account for all of the energy. We can't make energy up out of thin air. It's balanced. In the context of energy available for evaporation, only a small, let me back off that statement. The plants store only a very small fraction of the energy that's absorbed, that's provided by the sun. It's either stored in chemical bonds or as heat. So what we're going to do in the context of the energy that's available for evaporation and driving the plant temperatures, we're going to ignore the amount of heat storage and metabolic storage in plants because it's small. It's small compared to the rest. It's not that it's unimportant. It just does not contribute much to the evaporative process in a leaf. So we're going to ignore the storage. So that then shows that the energy plants gain from the environment is matched by energy losses to the environment. Gains equal losses. It must be so. So how is this balance achieved? And it's achieved by changes in plant temperature or leaf temperature until gains equal losses. When Russ walks outside and the sun is shining, how is his head going to feel? How's your head going to feel, Russ?
Nice and warm.
Nice and warm. What's happening is that the temperature on the top of the head is increasing until the energy Russ's head is gaining from the environment is balanced by heat that's being lost to the environment. That's what happens in plants. That's the primary driver of, or that's how plant temperature is involved in all of these processes. Plant temperatures change until gains equal losses. So we're going to look at some of the fundamentals of how that occurs. First thing, we want to give you an insight into how we describe this energy exchange. We describe it as a flux density, which is the amount of energy in joules that is being received or lost from 1 square meter of surface area every second. That's called an energy flux density. So it's the energy flux, which has units of joules per second. Joule per second is a watt. The output from a 60-watt light bulb is 60 joules of energy every second. It's the amount of energy per time reaching 1 square meter of surface area or leaving 1 square meter of surface area, because I'm going to show you some examples later on. So the units are going to be watts per square meter, which is a joule per second per meter squared. It's also important to note that everything that has a temperature above absolute zero is emitting electromagnetic radiation. You and I and plants are emitting electromagnetic radiation. We can't see it because the wavelength of that radiant energy is too long. Our eyes are not sensitive to that. But everything is emitting electromagnetic radiation as a function of the fourth power of the surface temperature. So Russ, who has a surface temperature of her skin right now is about 31 or 32 degrees, is emitting electromagnetic radiation as a function of the fourth power of his absolute temperature. Okay?
Hopefully it's warmer than 31 or 34, right? Because this is Kelvin.
It's 34 degrees Celsius, but you got to convert that to Kelvin, so 303, 302. He'd be toast. Degrees Kelvin. Thanks, Seth. It's also important to note that the wavelength of emission is inversely proportional to the temperature, so that hot objects emit shortwave radiation, cooler objects emit long-wave radiation. The sun, which is hot, emits shortwave radiation. About half of the radiant energy emitted by the sun is visible light. You and I, plants and soils emit radiation that's long-wave radiation. We sometimes call that thermal radiation. That's what an infrared thermometer measures, such as this. Amir may be out in the field and pointing at some plants, and he's reading a temperature. Well, what happens is this device is measuring the long-wave radiation emitted by the plants and converting it to an approximation of surface temperature. That's what this device does. Now, the question for Amir is, what does that temperature mean?
It ignores the short wave, though, right?
Yes, no short, no, just long wave for the purpose of getting a temperature. The question is, what does that temperature mean? You might have this plot having a temperature of 30 degrees Celsius, this next plot over here having a temperature of 32 degrees Celsius.
The difference between it and the air temperature.
Well, yeah, but we'll come back to that. And the question is, what does all of this mean in the context of something that's relevant to the plant? It's very easy to go out and do this measurement, but what does it mean? What does it mean? Oh, shoot. We'll get to that.
It's really about transpirational cooling.
Yes. The other thing that happens, of course, is that leaves reflect, in addition to emitting electromagnetic radiation, they reflect, transmit, and absorb electromagnetic radiation. The energy balance and photosynthesis are controlled by the amount of radiation that is absorbed. Remote sensors in a drone are going to be measuring solar radiation that's reflected from the plants. Or if they're measuring temperature, they're measuring radiant energy emitted from the plants. And typically what's done in the context of remote sensing in the visible and the near IR, they're using that information to get an estimate of leaf area index through something that's akin to, in this case, the normalized difference vegetative index, or at very specific, using hyperspectral data at very specific wavelengths to get an estimate of something that's called the photochemical reflectance index, which is related to light use efficiency. So you can gather information about what's happening in the plants. But you've got to remember what you're measuring is the amount that's being reflected or emitted. What complicates this is that absorption, reflection, and transmitted in the context of a leaf are highly dependent upon wavelength due to plant pigments and structure. So the amount that's reflected, absorbed, and transmitted depends highly on pigments and structure. And of course, all of you know that most of the visible light, or a high proportion of the visible light, is absorbed by plant leaves. Not only is the amount reflected, transmitted, and absorbed a function of wavelength, but so is the amount that comes in from the sun. The curve in the red shows the flux density of radiant energy incident at the Earth's surface as a function of wavelength. Very high fraction is in the visible region. So not only is the amount reflected a function of wavelength, the amount coming in is a function of wavelength. And so the amount that you measure with a drone is a function of how much is coming in and how much is being reflected. And it varies with wavelength. Yeah, Seth.
So on the energy at Earth's surface, all the valleys in that red line compared to the solar output, is that due to water absorption?
Yeah, due to absorption bands. Some of it to water.
Some of it's water, not all of it.
Yeah. And there have been people that have been looking at hyperspectral information at water absorption bands as a possible indication of plant water status. And I have looked at that as well, but it was a long time ago. Okay. But that's not all. The flux density that is incident on the surface depends upon the angle of the surface with respect to the sun. The closer the surface is to being perpendicular to the solar beam, the greater is the amount of radiation incident upon a leaf. Now, is a leaf flat?
No.
They're not flat. They got all kinds of facets pointing in different directions. That means that the amount of radiant energy reaching a leaf is going to be highly variable on an individual leaf because of the position of the sun with respect to that surface. Again, if that surface is facing the sun, it's going to be getting a lot more radiant energy than if it's flat or facing away from the sun. And what would you think the implication of this is for the temperature of an individual leaf?
If it gets the full amount of it, it will be hotter.
Right, but at an individual, what would you think this does to the variability of the temperature on an individual leaf?
It's the variability.
And it gives variability to the leaf temperature, exactly. And the position of the sun with respect to the leaf is changing throughout the day. Okay? And so now we're going to look at the energy balance. In simple terms, as we said before, that the energy input is balanced by energy outputs. And we're going to have three mechanisms of energy output. One is emission of long-wave radiation. Another one is through the process of convection. Moving air passing over the leaf is going to pick up heat from the leaf and carry it to the air. Or if the air is warmer than the leaf, moving air is going to bring heat to the leaf. And the major energy dissipation process is through evaporative cooling, through the evaporation process. That is the major cooling mechanism of the plants. So let's look at this now.
And pure reflectance itself is energy dissipation, right?
It is, but
Not
we're
absorbed. You're reducing the energy load.
well, yes, but we're, as you see right now, we're talking about what we're concerned about is the amount of energy absorbed.
Right.
That's what matters in terms of the leaf energy
Do
balance.
these vary significantly by genotype? You know, the difference mechanisms for dissipation?
They could, depending on leaf size, leaf
We're
orientation.
measuring the long wave radiation, right?
But the long wave, yeah. Save that question, Amir.
Okay.
Okay, we're going to come back to that. So I'm going to use a sign convention. I'm going to say that energy gains to the leaf are positive. Energy losses from the leaf to the environment are going to be negative. Now we're going to look at this whole process in a little bit more detail. And then again, you can ask questions, and I'm going to ask you some questions. So the energy balance of the leaf says that the net radiation, will define each one of these terms. The net radiation plus the latent heat flux, which is the energy contained in the water vapor that diffuses from the leaf to the air, plus the convective transport of heat from leaf to air through moving air, plus the storage term equals 0, but we're going to neglect that storage because it's small. Okay, in the context of what we're interested in, a driver for plant temperature. It is the energy balance that links the plant to its environment. Plants respond to the changes in the energy balance, and that links the plant to the environment in which it's growing, the above ground environment. Later we'll show how that's linked to the below ground environment. So, the net radiation consists of several terms. Leaves receive shortwave radiation from the sun, from the sky, and long-wave radiation from the atmosphere. The atmosphere is emitting long-wave radiation. Part of that sunlight is scattered and comes in as blue light. And leaves also receive shortwave radiation reflected from their surroundings by other leaves or from the soil, as well as long-wave radiation emitted by their surroundings. And leaves also emit long-wave radiation. So the net radiation is the sum of all short and long wave radiation is absorbed by the leaf, minus the amount that's emitted. That net radiation is available to drive the evaporative process in the leaf. It's available to increase the temperature of the leaf. And some of it's used in photosynthesis. The net radiation is positive during the daytime and negative at night because there's no sun, obviously. So a large portion of that net radiation is consumed by evaporation. When plants have access to available water in the soil. And again, we'll look at this in more detail. Most of the remainder is lost as heat to the atmosphere. So the plant has access to available water. Most of that available energy is going to be consumed in the evaporation process and lost to the atmosphere as the water vapor leaves the leaf. Evaporation is fundamentally a cooling process. It cools the plant. In areas where it's arid, such as the high plains of Texas, you can often find situations where the leaf temperature is lower than the air temperature. And so you have the leaves actually extracting heat from the air. The direction of and we'll look at this, the direction is always of heat transport is always from high temperature to low temperature. So if the leaf temperature is lower than the air, the direction of the energy input is going to go from air to leaf, which makes your interpretation of leaf-air temperature differences complicated.
That's why we live in Sudan. If it wasn't for the trees, we would have died from the heat.
So, great. Maybe I'll just use the keyboard. So if available water is low, less of that available energy is going to be used in evaporation and more in heating the leaf and being lost to the atmosphere in terms of convection. The next term I want to look at is the one that's related to the transpiration process, and that's the latent heat flux. That kind of washed out there, isn't it? In the process of transpiration, water evaporates from the cell walls, diffuses into the intercellular air spaces. That water vapor then diffuses through the stomatal opening and through a layer of relatively unstirred air that we call the boundary layer. The stomatal opening and the boundary layer are impediments to diffusion of water vapor from leaf to air. And we describe that impediment as electrical analog, so we talk about stomatal resistance and boundary layer resistance. So water vapor diffuses from the interior of the leaf to the air. What would you guess drives that process? Pardon me?
Yeah.
I didn't hear.
He said vapor pressure deficit.
Not quite. Not by the classical definition of vapor pressure deficit. But you're close.
Evaporative demands.
You're close. You're close. We're only going to focus right now on this term in the bracket, which is defined as transpiration. Transpiration is driven by the difference in water vapor concentration between leaf and air. It's the water vapor concentration between leaf and air. And imposed on that process are stomatal resistance and a boundary layer resistance. And we would typically describe the units for this would be grams of water vapor per second per meter squared of leaf area. If we multiply that by the energy content of that water vapor, we get the latent heat flux. That puts it on an energy term. That energy that's contained in the water vapor is energy that the water absorbed to break the hydrogen bonds between molecules, overcome surface tension, allowing that vaporization process to occur. Typically, at 20 degrees Celsius, the energy content of 1 gram in water is roughly 2,450 joules of energy, and that is a lot of energy. For reference, the surface of the Earth during the middle of the summer at noon will receive about 1,000 joules per second per meter squared. This is a lot of energy contained in the water vapor, which is why this process is a cooling process. And the boundary layer resistance is affected by wind speed and leaf size, which we'll look at later. How many of you use weather station data that has relative humidity or do a relative humidity measurement? I don't know how many of you do. Relative humidity is irrelevant. Plants do not respond to relative humidity. Relative humidity is only an index of how saturated the air is. Plants do not respond to relative humidity. They respond to the water vapor concentration in the air surrounding the leaf compared to the water vapor concentration in the interior of the leaf. That sets up a whole host of processes.
But isn't it going to be lower in humid areas?
Yes, and we're going to get to that next. Yeah. That's a good point, Amir. It's important to note that the water vapor concentration in the leaf is related to leaf temperature. The higher the leaf temperature, the higher the water vapor concentration in the leaf. And that relationship is not linear, it's sort of exponential, which makes transpiration a very sensitive process, a process that's very sensitive to leaf temperature. The final term is that convective transport of heat, driven, that we call sensible heat, that's driven by the difference in temperature between the leaf and the air, multiplied by the volumetric heat capacity. The product of volumetric heat capacity and temperature is a heat concentration. So the convective transport of heat, driven by the motion of air, or caused by the motion of the air, is driven by the difference in heat concentration between leaf and air. And when the temperature of the leaf is lower than the temperature of the air, sensible heat adds to the energy that's available for evaporation. Okay? Now, the important thing to note is that the sum is 0. Okay? So if you change anything, any component of any one of these terms, it's going to affect everything else. It's balance. And so let's look at that in more detail. So the energy balance says that the net radiation, which is absorbed short and long wave radiation minus the amount emitted, plus the energy that's contained in the water vapor as it leaves the leaf, the latent heat flux, plus the sensible heat flux driven by leaf air temperature difference, is equal to 0. So where do you see leaf temperature being shown explicitly? Which two terms?
Sensible heat flux is one of them.
Sensible heat flux is one. There's leaf temperatures there explicitly. What else?
Net radiation.
Net radiation. Do you see it explicitly in the latent heat flux?
No.
Is transpiration affected by leaf temperature? And what does leaf temperature affect? The water vapor concentration in the interior of the leaf. So when Amir goes out and he measures leaf temperature, that temperature is a function of all of this. It's a function of all of this. It's a function of the net radiation. It's a function of the latent heat flux, and it's a function of the sensible heat flux. Any change in anything in these terms is going to affect everything else. So leaf temperature fundamentally is something that's pretty complicated. So let's look at some scenarios, and Amir alluded to this. So Wayne Smith is growing, and notice that there is a minus sign to indicate that if it's away from the leaf, it's going to be minus. If it's towards the leaf, it's going to be positive. But that's not the most important part at the moment. So Wayne Smith is out, got cotton plots out in the Brazos bottoms. What's the humidity like around here? And he's got some, and for reference, he's got some cotton plots that are up in Lubbock. Okay.
90%.
So, would you expect there to be higher water vapor concentration in the air here or in Lubbock?
Here.
Here. What's that going to do to this difference?
Make it smaller.
Make it smaller. What's that going to do to the transpiration?
Make it lower.
Make it lower. Exactly. What's that going to do to the leaf temperature? Remember, evaporation is a cooling process.
Make it hotter.
Make it higher. Exactly. And now you go to Lubbock and say everything else is the same except for the water vapor concentration in the leaf. And so this term is going to be lower. That water vapor concentration is going to be higher. The transpiration, therefore the latent heat flux is going to be higher. What's going to happen to the leaf temperature? Because evaporation is a cooling process.
It's going to get lower.
It's going to get lower. Exactly. That's what makes this interpretation of temperature a rather complicated process. And so in the case of Lubbock, you can typically have situations where, because of evaporative cooling, the temperature of the leaf is lower than the temperature of the air, so that cotton is actually extracting additional energy from the air and using it to drive up the water use. Now, let's suppose you get into a water deficit situation and the stomata start to close. What happens to this resistance? Remember, resistance describes how easily the water vapor will pass through the stomatal opening.
That makes conductance lower.
And which means the resistance is higher. Okay. So if this gets higher, what happens to the transpiration and the latent heat flux?
Lower, heat increases.
Gets lower, temperature goes up, more of the heat is being dissipated as sensible heat. So we know all of this. The question is, how do you interpret that in the context of a measurement of temperature that you're taking? That becomes, and we'll get to that in a minute. But typically what's done is that, as Amir said, they'll go out and they'll take a canopy air temperature difference, not an individual leaf, but the plant canopy temperature. They'll take canopy air temperature difference, and that difference is a function of, in this case, as you mentioned earlier, vapor pressure deficit, which is an indication of the water vapor concentration in the air with respect to what it would be when the air is saturated. So the drier the air, in this case, depending upon where you are, in this case, the leaf canopy temperature gets lower and lower as the humidity deficit in the air gets higher and higher. A friend of mine, Ray Jackson, developed this concept and published this in 1981. Did a thorough analysis, and this has led to something that's called the crop water stress index, which is used sometimes in irrigation scheduling. So, another thing that you need to be concerned about,
Go back to your equation. I just want to make sure we got everything in there. So, are there known catalysts for increasing water to vaporize more quickly within the leaf, or do solutes or carbon dioxide play in that?
Solutes can affect that, and solutes can lower the humidity. But typically, what you have the water on cell wall air interfaces that has gone through the plasma membrane, so the solutes are not there. So it's water that's held under tension, and that is definitely going to affect the ability of the water to vaporize. But the thing about that water is that it's not containing solutes at this point. It's come up through the xylem, passed through the cell, through the plasma membrane to the cell wall, so there's kind of a thin film of water, and I'll show a slide of that next week.
So thinking about other genetic differences in these, I mean, is there ways that certain plants would be able to better increase the vapor than the plant next to them? Because we're sort of holding that constant in this case.
This term,
the one next to it, right?
this one?
Yeah.
Well, it's really not constant. It's a function of the temperature of the leaf.
Right. But is there any genetic differences that aren't being accounted for in this?
I don't know the answer to that. I mean, presumably if you have...
Like a catalyst, for instance, would increase the ability for the air.
No.
So internal anatomy could have an effect. Stomatal density could have an effect on.
Well,
stomatal density is
stomatal
there.
density affects the rate at which the water moves through. It doesn't affect the evaporation itself.
First, but it affects the rate, right?
Yes, affects the rate.
Which is is equated in the latent
Right.
term.
Right.
Well, you
Yes.
see where stomatal density is there, but if there's any other anatomy that...
That's resistance. That's not density. That's just
Okay.
aperture.
This is a function of the size of the stomatal opening and the number of stomata,
Okay.
number of stomates on the leaf. So it's a function of both. Yeah, Lloyd.
Yeah, on a cool season forage, whether it's wheat or ryegrass, even if you get frost in the morning and it gets over 40, 45 degrees, on a sunny day we're getting vegetative growth. Now, so we're looking at that from a different standpoint. We want that. So all these rules and regulations still prevail.
It applies to you. It applies to the plants. It applies to animals. It applies to everything, because basically a lot of the processes are the same. It applies. The energy balance, every object, everything has an energy balance. And so it applies. Just briefly, one thing, let me skip. I'll come back to that next week. How much variation, given everything we've talked about, how much variation would you expect to see in the temperature of an individual leaf?
Throughout the day, you mean? Or?
One time.
Between genotypes?
One leaf. On one leaf.
On one day.
On one leaf. Remember all the things we've talked about. Illumination geometry.
Yeah.
What I'm going to show you is a thermal image of a soybean leaf. There's about a 1 degree difference in temperature across the leaf. Remember I talked about there's this boundary layer of still air. The boundary layer is thickest in the interior in the center of the leaf and thinnest on the edges. I'm guessing because this is cool here that the air is moving in this direction. And so the result of this is about a 1 degree difference in temperature across this little leaf. Okay?
And the wheat leaf also rolls.
Exactly.
That can also make a lot of change.
Yeah. So one more thing, and then we'll quit for today, and then we'll continue on next week. Here I have an image of maize plant, and this is the thermal image. Temperatures ranging from about 27 degrees to about 33 degrees in this one little spot size. Okay? My question, what's the representative leaf temperature? How many IRT measurements do you need?
I don't know, some of it is shaded and it's pure.
Yeah, exactly. Where should the IRT be pointed?
The sunny area.
Why?
Because it's always in the, the leaf is assumed to be in the sun, facing the sun.
Why?
That's how it gets the solar radiation.
Well, but not all leaves are in the sun. The part of the leaf may be in sun, part of the leaf may be in shade. And it's changing throughout the day.
That's right.
And then what does an IRT measurement in the
Maybe take
mean
measurements of
in the
everything,
context of plant? What does it mean in the context of plant stress? So I want to caution you, those of you who are doing those kind of measurements, one measurement is not sufficient. It's essential to know the field of view of your infrared thermometer. How big of an area are you looking at? Theoretically, I could come up really close to the leaf right here and take a measurement of an individual leaf. But what am I doing?
Taking one leaf.
But what am I doing to the leaf energy balance?
You're shading.
I could be shading it. I am a source of long-wave radiation. This is a source of long-wave radiation that is reaching a leaf and changing its energy balance, which is why we don't use something like this to focus. You can't take a temperature measurement of an individual organ, an individual leaf.
Yeah. You know, it's there, but like half a meter.
Yeah, but so you're standing a half a meter away. You're getting some sort of
45 to the horizontal, 45 to the vertical, half a meter.
What you're doing by holding it at an angle is you're minimizing the influence that the soil is having.
Exactly. That's right.
But you may be having as much variability within plots as you could have between plots.
The environment's is too unstable around here to even use that.
Yes.
The wind's always changing, the clouds are changing.
Winds, but that's happening everywhere. The environment,
Right. So
the key in all of this is that we haven't linked it to the soil yet. But the key for all of this, it is all about the energy balance. It is the environment in which plants grow that is dictating what happens to a plant. Okay? That's the take-home message. And you've got to be cautious. As I said at the beginning of this, Dr. McGinnis and I are resource people. Perhaps we can help you reduce the error bars on your measurements. And again, we're going to continue on with this next time. But I would encourage all of you, or as many of you as possible, to take the biophysics course that Dr. McGinnis teaches. The fact that it has physics in the title does not mean it's difficult. But it is a way of really looking, it is a way of, if you want to understand plant behavior.
Are you talking to students?
Students.
To everyone?
Well, you mean, we're all lifelong learners, right?
Sure.
But again, plants grow in the real world in an environment that is constantly changing. And so if you want to truly understand plant response and stress, you really need to understand the mechanisms by which plants interact with the environment. Perhaps it can we can avoid some issues if we are cognizant of that. Okay. The same question, I started doing this, my PhD dissertation in 1974. We still have the same question. What do these measurements mean? What do these measurements mean in the context of something that's relevant? We get a lot of information. The question is, does it matter? We can get a lot of information. The question is putting it in the context of something that is relevant to making plants withstand drought and still produce
Yeah,
an economically
I have
viable yield.
yes, a comment about this. You take thousands of measurements on different genotypes, and the temperature varies through the 2 hours that you use. And so you cannot just rely on this pointer. You have to also couple it with powerful statistical designs, such as an augmented design. You need to use moving means analysis, nearest neighbor analysis.
And
So
I
this-
would say you also need to couple it with physiological measurements.
That's right, and you need to have a reference of the date of the air temperature all the time. Because sometimes you just take the plant temperature.
Okay, that's while we're doing that, if you're talking about plots. What the air temperature in a plot is affected by whatever is upwind of that plot. So if you've got a weather station measuring air temperature, that air temperature is different than the air temperature that is relevant to this particular plant. So that's part of the complicating factor as well. So I don't want to scare you. It's just this is the real world that you've got to be very careful about interpreting your measurements. You're taking we can take a boatload of data. We have tremendous technology nowadays. The question is, what do we do with it? And again, come back to the term. The question is, what does it mean?
Actually, I would say that sort of the mentality on that might have changed a little bit over the last few years, because if you can collect a boatload of data and you can do it cheap enough, and you can correlate it to something, we don't necessarily need to know what we're correlating it to as long as it's predictive. I mean, that's the whole idea of
Right.
spectroscopy, right? So it does depend what your goal is. But
Right. But if you want to then take the next step and says, okay, how is it going to behave in this particular environment? It's a function of what that environment is imposing on the plant. Yeah, I wouldn't disagree with you in the least. It's just you need to be cognizant of this, that it is a highly dynamic environment in which plants grow. Yeah, Dirk.
And developmental stage has a big influence on the temperature.
Yep.
Whether there's carbon demand, rapid
Well,
conductance.
In terms of perhaps the model conductance, in terms of the energy balance, that part is a small part of the. Yes, everything is relevant. You're doing a plot study. Row direction is relevant.
So do you,
Row spacing
does-
is relevant. Everything you do in terms of the construction of the plots is relevant to creating an environment that is unique to that plot.
So would a remotely sensed IRT be preferable? You can catch the whole plot at once rather than worry about environmental noise of moving.
Thermal camera.
I think everybody, except for Matthew Reynolds, who has a desert environment that's very steady, has dismissed using IRT just because it's so variable.
Well,
You can't get anything consistent.
if you've got a thermal scanner, you still have that variability. Plus, if you're looking down, you're also seeing soil.
Right.
So, and you're seeing you're still seeing shaded leaves, and you're seeing sunlit leaves.
But you get a plot average.
You can get a plot average. The question is,
Preferable a little bit.
the question is, what does it mean?
Right.
Well, it's just one trait, and we look at tens of traits.
Right.
It's a good integrative trait of all other functional physiological traits. though.
But when you
IRT
take
is kinda integrated.
you take your varieties to the field,
Yeah.
all of this.
Yes.
If you're doing this initial screening in a greenhouse, and you're making decisions in a greenhouse with infrared heaters, for example, to heat them up, and then you go to the field, well, you're going to get quite easily get a completely different response.
Exactly.
So it is just be aware of the fact that this is highly variable. Wayne.
Jim, I know, and Kevin can answer as well, and for the students in here. I know that as technology improves, we become more sophisticated with the measurements we make and how many measurements we can make and those sorts of things. But does anyone know of a plant breeding program that has a physicist type like Jim and Kevin involved in the program itself in the way of designing and the measurements they take and those kinds of things?
Well, Bear Crop Science actually now is hosting Matthew Reynolds, and he might be hired by them actually.
He's a physiologist, but not a physicist.
Okay.
Physio.
But he has he has some of that knowledge too.
So, we've added over the years, we've added, this concept that we don't have plant breeders out there anymore. We have plant breeding teams, and there's an entomologist, there's a pathologist, there's a bioinformatics guy, and there's a genomics guy. And so I was just wondering if we had does anyone have an experience where this became an integral part?
We need to be the first team,
Design
I
and
guess.
selection.
You know what? But when you look at something like what cultivars are grown, right, across Texas, at least in maize, I'm guessing in cotton, you have huge differentials in temperature and humidity, but that doesn't change which cultivar does the best, right? So to me, that sort of suggests that maybe those factors are less important than some of the soil, some of the day length, some of the other factors in terms of.
Well, to me, it suggests that so far, and this may indicate again how how gross measurements are, genetics is overriding this stuff. When we pick something that does good, it's adapted to a geographical area, and so within that geographical area, there's all this variability, but the genetics are overriding that.
If you're
I was
concerned,
wondering if there was
Genetics is
anyone that
regulating
looked within
that
one of
function.
those and said, okay, now we're going to be more precise and utilize, because it seems to me that just as you guys have said, well, this gun doesn't make any difference, we shouldn't be using that. I assume as we move to this high throughput bid type, there are going to be those kinds of data that we're just going to get running out of our ears.
what if conservative use of water is one of your criteria, because water has become limiting?
A cooler plant is usually
Yeah,
less water.
but we put water on in such a gross way. I mean, if I'm going to put on 5 inches today, it really doesn't matter if it's 4.5 inches or 5.5
But that's
inches
going,
right now.
that's going to change. Those days are over.
Well, it might. I wouldn't say those days are over.
One of the questions,
Next year will be a rainy year, and no one will talk about drought.
one of the questions that I asked early on in my dissertation research is in the context of using temperature as an indicator of stress and doing well under stress conditions. Do you want a leaf temperature that is low, or do you want a leaf temperature that's higher?
Yes.
Higher.
Exactly. I could say lower, because if you have metabolic processes that are going to be inhibited at high temperature, I'd say you want lower. But generally, the reason the temperature is lower is because it's using more water.
Well,
So,
in Sudan, I measured the difference of 10 degrees centigrade between a cultivar called the Libera and the air. So the air was like 35 degrees, Libera was 25.
right.
And
And
it was the best cultivar then. So
Just mining water from the soil?
yeah, it just uses irrigation water to put it.
yeah, that's the reason. That's the reason. Again, I mean, all of you know this. What does well under well-watered conditions may not do so well when you have water stress conditions. And so the same questions seem coming around and around and around. And that's what makes this so much fun. So next week, we'll finish up with this, and then Dr. McGinnis is going to take over, and we're going to talk a lot more about the soil environment and the soil water part of it, and how what happens and how the available water is linked to the energy balance, and then some of the issues you run into when you try to go in the greenhouse or in the field and determine water use by cultivars, water use, the amount of water used, all that kind of stuff. So, again,
My question about the fact that this gun measures long waves. I mean, we know that there are short waves and other sources of dissipating heat. Or we're just measuring one source, right?
well, the major radiation dissipation mechanism in plants is long wave emission. Reflection, most of the visible light, for example, is absorbed.
Okay.
And so, I mean, in the near infrared region, there's more reflection. But the major way of dissipating heat by radiation is emission of thermal radiation. And you're all witness to that. The surface of the Earth cools at night. The reason it cools at night is there's more long-wave radiation being emitted out into outer space than is coming in from the atmosphere. So the surface loses energy at night. It's through the emission of the long-wave radiation. So we'll continue on with this discussion next week.
Thank you.